All right, let's get started. Welcome, everybody. Thanks for coming the rain. I ruled you here by saying that as a professionally trained magician, I have some good tricks to show you. So I thought it'd be better to not let you down. And so let me start with the trick. Pretty cool trick. Got two decks of cards, right? A blue one and a red one. Would you like to choose one? Which one do you like?
The deck? The red one.
The red color, right? So
Okay.
you like it. You can keep that
Keep the deck? Okay.
for now.
Okay.
Look, the other deck.
Okay.
I'll take the deck out of the box. One, two, ta-da. Is that cool? Where's the
That
box?
is.
The box is here. So that's a very basic magic trick. Well, it's not over yet. Hey. So we just got started. So I just took all the cards out of the box, and next, this is a blue deck, right? The color is blue. And so this talk is all about changing colors. I'm going to change the color from blue to red. Look, one, two, ta-da. Is that cool? Where's the blue deck? Well, open your box. That's called transformation. Is that cool? Yeah. So that's the first trick. Your job now is to do a move to a front shuffle. That is, you find the ace of hearts to five of hearts. Move them to the front. We're
Move
going to
them
use
to
that
the front?
later. Yeah, you have about 10 minutes to do that.
Okay. Just on the top of the deck.
Yeah.
Ace of hearts and five of hearts.
Yeah.
Okay.
Ace of hearts, two of hearts, three of hearts, da-da-da, five of hearts.
Oh,
That's your job.
all in order.
Yeah.
Okay.
As you will see, the order will matter. So that's a cover I designed. And if you scan this QR code, you're gonna find the notes of this talk, the notes I wrote. So you can scan it or take a picture before I scroll down. Take this talk very seriously, and I made a 19-page note file, PDF file. So let's get started. Also later, I promise I'll change this deck back from red to blue for the end of the talk. So let's, I've divided this talk this way into a few acts. So let's start with the first act. Act one, the magic of coupon collecting. So it's better to start with a familiar anchor that is something you've been familiar with. The coupon collecting problem is, has a rich history. And so let me first introduce the history to you. The coupon collector problem goes back to at least to Laplace. A major modern milestone is Erdos and Rennie's 1961 paper on a classical problem of probability theory. It's a pretty recent paper. And for group drawings, the key references are Stagge's 1990 paper, The Collector's Problem with Group Drawings, and Henz's 2021 paper, Two Poisson Limit Theorems for the Coupon Collector's Problem with Group Drawings. So that's a brief history. And later I'll show you how this is connected to today's topic, top-end random shuffle. So first of all, let me tell you what this shuffle is. What do you mean by a top-end random shuffle? Let me give you a small example. Say M is 3, so we do a top 3 to random shuffle. So it works this way. Suppose we have 5 cards, 1, 2, 3, 4, 5, and we take the top 3 cards, makes sense? The top 3 cards, and randomize the order, and then put them back, insert them to the rest of the deck, say 4 and 5, uniformly at random. So that's a top-end random shuffle. I'll do a demonstration in a few minutes. And let's instead of analyzing this shuffling process, let's consider the auxiliary process, which is the coupon collector problem. Suppose we have several rounds, and each round chooses an independent uniform M subset. We call this M subset S sub T, which is a subset of the set of the first n integers. And the order is M, of course, because it's an M subset. So let's define the number of coupon types that are never chosen after k rounds to be this letter E. I use the letter E because you can also think of that as the ball box model. E also can represent the number of empty boxes. So here, let's use the coupon setting to be consistent. And this E is defined to be n minus the coupon types that are chosen, right? So the difference is the number of coupons never chosen. And how to use that? Well, let's define this probability of this set E equals U to be this piece of K, superscript M. This is a pretty funny symbol. I use this to denote this probability just to be consistent with my paper. So this is a small example in my paper. This is, you can find a more general setting. And this will make more sense. But whenever you see this in this talk, it just means this probability. Next. To further compute this probability, we can make use of a few cool formulas. The first one is the inclusion-exclusion formula from probability, which looks like that. We can directly use that. This comes from this paper, one of the papers that I just told you, the collector's problem with group drawings. And by this formula, we're able to simplify this probability and compute their values for different U values. So here, if you let U be 2, you're going to get this probability by this inclusion-exclusion formula. Makes sense? So that's the whole process. And that also explains why we use the coupon collector setting to analyze the top amateur random shuffle. Because what's cool about that is that this, as I said, this is a familiar anchor. This enables you to use a rich set of known conclusions, like bundled conclusions, and directly borrow from that setting, coupon collectors setting. This is one example. So now we're able to compute, we've already computed these 3 probabilities. Notice, let me give you an example. Example 1. After 1 round, that is, notice K denotes the number of rounds. K equals 1, it means the first round. So after 1 round, when K equals 1, by the general formulas, we get this special case, right? So you can find there are the 3 probabilities, which are these 3, 0, 1, 2. They are 0, 0, 1. What does that mean? Well, it means after one round, the complete coverage is impossible, and 1 missing label is impossible. 2 missing labels occur with probability 1. So that's what it means intuitively. If you don't understand, let's use another example. After 2 rounds, when K is 2, the probabilities have changed. That is, after 2 rounds, we have these 3 probabilities. There's no 0 anymore. That means all 5 labels have been seen with probability 3/10. And exactly 1 label is still, missing with probability 3/5. And exactly 2 labels are still missing with probability 1/10. So, just a special case of the general proposition. But that's all. That's all it is. And so from this example, we can easily tell that K equals 2. This is the first time complete coverage becomes possible, meaning there's no non-zero probability here. And so after this example, we have a lot to cover today. I hope to cover the first 4 acts. We've got 6 acts, so I'll focus on the first 4. And we can just glide over these 2 propositions. They're also from textbook examples, and they're known results from the bundled results. So suppose this T upper superscript M is the cover time. What does that mean? Well, it means the first time all N labels have been chosen or have been seen, which is rigorously defined this way. The next proposition gives you the exact expression of the cover time, which is this expression. And so actually these 2 propositions, we have the expectation of this random variable takes this form. In particular, if this is the usual coupon collector problem with M equals 1, in other words, if we only choose 1 coupon each time, the most common one, for the generalization, we have this expression. The expected value is pretty easy, right? Just n times this sum. Likewise, we have this probability is less than or equal to this number. So the significance is, you see this number, right? N over m log n plus c. This number will play a big role, an important role later. I'll explain to you in Act 6. So I'll just point this out here. This time, this comes from the setting of the coupon collector problem. Finally, we have one last proposition, and this is probably the most popular proposition in the coupon collector problem setting. That is, if we set k to be this number, which is the same number here, of course, the floor and the ceiling doesn't matter too much, and we have let e. So that is the same e, just to indicate that this e is dependent on n, meaning the number of cards or number of coupons or the number of coupon types, right? Just to indicate they're related to each other, we add a subscript n. This is the same as e, just to tell you that each round e is different. I mean, for each n, e is different. So we have this en, meaning the number, this random variable, converges to Poisson of lambda weakly. So that's a pretty popular proposition. If you know probability, if you've taken, I don't know, 50, probably not 507, but 607 or 605 topics in probability, probably you've learned that. Yeah, now you've seen that, right? Yeah. It converges to the Poisson random variable weakly. In other words, because everything is integer valued, this is equivalent to this, meaning the probability mass function converges to the PMF of the Poisson random variable, Poisson of lambda. So yeah, they're equivalent. That is Act 1. Coupon collector problem. Next, let's move on to the next act. I'll tell you how this coupon collector problem setting is related to the top M to random shuffle. So the title is called The Magic of Adding Colors. Also, I'll add colors to the picture. Let's just run a quote unquote driving simulation. If you were in my education seminar 3 weeks ago, you know what this means. The driving simulation means a special example. So I'll just use this special example, the toy case, to organize this talk, to tell you what everything means. So I'll introduce a lot of symbols. Let me first tell you what the top M to random shuffle with colors means. Let's just use 5 cards. So have you found the 5 cards?
Yeah, I think so. Here's the 5.
Yeah, you can keep that. Okay. And so we have, let's just use these 5 cards. 1, 2, 3, 4, 5. So ace of hearts, 5 of hearts. And so what is a move to front shuffle? Let's suppose the 5 cards are organized this way. So 1, 2, 3, 4, 5, right? And this is the first card. This is the second card. In other words, the first card is ace. The second card is 2. Makes sense? And let's do a top three to random. Actually, before we do that, let me tell you what color means here. You can use, color can mean a lot of things. You can let this be the red color and you have black color. But here, because the color is 2, the number of colors is p equals 2. So I just take this case, p equals 2, and interpret the 2 colors as back and face. I think that's the most natural interpretation. So let's say the first card is face down, right? So let's just interpret that as color 0. In other words, color 0 is the default backside, and color 1 means face up. So let's interpret that this way. This is easier to understand. So top M to random shuffle, in this case M is 3, so top 3 to random. It means we just take the top 3 cards and randomize their order. So whatever you want, shuffle them, make them all mixed up. and then add one step, randomize their color. What does that mean? So we just flip that uniformly at random and flip this. You can keep this face down. And then we insert the 3 cards back to the deck like this, including the top position, right? 1, 2, 3, right? That's one step of the top 3 to random shuffle. Does that make sense? So now the order is 2 with color 1, 4 with color 0, 8 with color 1, 3 with color 0, 5 with color 0. And all of these arrangements form the state space of this chain. So this is the state space. This is not, if we don't consider the color, then the state space would be just S5, if you know the general top to random shuffle. The state space would be S5. But now, since colors are in the picture, we have, this is the read product of C3 and S5. What does that mean? Sorry, C2 and S5. C2 is just another way of saying the cyclic group Z mod 2Z, or Z sub 2. For those of you who are algebraists or algebraically minded, that's what the read product means. This is just another way of saying the semi-direct product. The semi-direct product. Actually, the arrow should be faced this way, right? Should be yeah. Just a kind of semi-direct product with. So the semi-direct product, the underlying set of the semi-direct product is the same as the underlying set of the direct product, or the Euclidean product. You can think of it this way, except that the product rule is different. So that's how we define the product. If you don't understand, you can just ignore that. And why do we use the semi-direct product? Well, because the direct product means we have independent pieces of information, but the semi-direct product means one piece of information depends on the other or moves the other. Because here, the S5 refers to the order. SC2 means the color, so we have 2 colors, which are 0 and 1, right? And when you move a card, of course, you move the order, you change the order, and at the same time, you change the color, right? You change the color distribution of the deck. So they're related. You cannot use the direct product. Next. Of course, you can compute the order of this group, this product. So the order is 2 to the 5. What does that mean? Well, 2 to the 5 comes from this C2 to the 5th power, right? We have 2 colors for each component, so 2 to the 5. And we know the order of S5, this metric group on 5 letters is 5 factorial, right? So just multiply them together, that's the order. And the identity deck is, in particular, is this, 0, 0, 1, 0, 2, 0, 5. It means the original order, just a default setting. It means this 1, 2, 3, 4, 5, right? Organized this way. That's the identity deck. And for convenience, we can write this as this. We can write 0, 1 as just 1. If this was 1, 3 or 1, 1, we would write it as 1 bar. So that's a convenient way, I think, a pretty good way to simplify things. For example, we write 0, 3 as 3, and we write 1, 3, meaning if the card 3 with label 3 has color 1, then we write it as 3 bar. So that's another way. I like this way. So that's the identity deck. Next, let's define something. There's a lot of definitions. Actually, these definitions come from, not from me, but from a paper called Top Random Shuffles and Color Permutations by, I don't know how to pronounce the names, by Nakano, Sadahiro, and Sakurai, by these 3 mathematicians. Pretty recent one, written in the year 2023. So if you've understood all these definitions from this simple example, you'll have no problem reading this, no difficulty reading this paper. And let's also define this W35 as the frozen tail. In other words, W35, this, this looks complicated, but this just means this subdeck, the deck consisting of these two cards, 4 and 5. Because we're doing a top 3 to random shuffle, we randomize the first 3 cards, in terms of order and color, but we don't touch the last 2 cards. So they're sort of frozen. And so we call this the last 2 cards, the frozen tail. I use this name, the frozen tail. Actually, I gave it this name. I made this name, the frozen tail. It's inspired by this magic prop. This is, pretty good magic prop. I bought this from Amazon. And it's pretty fun. If you put a card here, it looks like an entire deck. So if you let the audience, let somebody hold this, and then you take away the first card, the audience will be shocked. So in their hands, look at this. So it's like the frozen tail. This is like a frozen tail, right? So that's why I call it frozen tail. Next, let's introduce something more. This B3 as the formal sum of all the shuffle products. Well, what does that mean? Intuitively, the shuffle product, alpha shuffle W35, where W35 is the frozen tail. It means the formal, it means let's say it this way. U, the shuffle product of U and V, means the formal sum of all the interleavings of U and V that preserve the relative order within each card. For example, the shuffle product of this word 231, or this card arrangement, with this W35, the frozen tail, is the formal sum of all these arrangements. In other words, we have to guarantee that W35, this order remains the same. We have to guarantee that the color remains the same. In other words, 4 must come before 5. And 4 and 5 must have no bar. They both should have color 0. Because the frozen tail should be frozen, right? So that's what it means. And we can manipulate the first two letters freely, like 2 bar 3 1 or 2 3 bar 1, whatever, the sum of everything. So that's the shuffle product. And when alpha ranges across the entire state space G352, because alpha comes from the first 3 cards, then the formal sum of everything is defined to be this B3. So intuitively, B3 means the sum of all colored words in which labels 4 and 5 appear in the order 4 before 5, both with color 0, while other labels 1, 2, 3 may appear anywhere in any order with any colors. So that's the intuition behind B3. And you can easily compute the order of B3. This is an easy combinatorics question. First, we choose the 3 positions of labels 1, 2, 3 from alpha, right? The first component. So we have 5, choose 3 options, and then we choose the colors. So there are 2 cubed colors, and then the order of the first 3 factorial. So that's the order of B3. And in other words, the summons, number of summons, there are 480 summons in B3. Next, let's define the support of B3 to be all colored words in which labels 4 and 5 appear in the order 4 before 5, both with color 0. Actually, that's by the definition of the support or formal sum. So if you define the formal sum this way, the support must be that, as you can tell, right? 4 must come before 5. That is the property of each summon, at each term. 4 must be before 5, and 4, 5 must have color 0. If one term doesn't look like that, if one term looked like 4 bar 5 or 5 bar 4, then it would not be B3. It would not be in B3. So it's not part of the support of B3. Does that make sense? So that's the idea.
So I guess what's really going on here is that basically so this guy is being treated as kind of a function from G32 to natural numbers, right? Or 0, 1 even.
You can think of it this way, yeah. Sure. Yeah, is everything okay? Next. Of course, we can, of course, again, if you're algebraically minded, you can write it this way, sigma inverse of 4, it means the position of the card labeled 4. The position 4 of 4 comes before the position of 5, right? Meaning the position of, it just means that. And it will have color 0. We define this set to be A2 because later we'll define other A's, like A0 to A5 in the next act. And that's basically the entire setup. And of course, finally, I think one last step in this act. Once the one-step law, Q superscript 3, we define this, in general, it's Q superscript M. And we define this to be B3 divided by the order of B3, where B3 is, we defined above, we just defined. So this means the one-step move is uniform on the entire support of B3. So that's the one-step law. That is another way of saying this. That is what it means by the measure. What it means to say the measure is uniform, right? So notice what I mean is the one-step law Q3, as we define here. This is not uniform on the entire state space. This is not uniform on G sub 5,2, as we defined at the very beginning. Why is that? Well, because no matter how you shuffle that, you cannot change the frozen tail. Does that make sense? 4, 5 must be like that. In other words, 4 bar 5, this can never appear. So of course, it's not uniform in the entire state space because this has probability 0. And as it turns out, it's uniform in this space, B3 divided by B3, it's in this space, the support of B3, which is a subset of the entire state space. Next, let me show you a magic trick for the next act. This is, this magic trick is pretty good at explaining the frozen tail. And so let me first, let's just use the 5 cards you picked. And, there are 5 cards labeled 1, 2, 3, 4, 5, of hearts. And let's, how long did it take for you to find them?
I don't know, like 1 minute, 2 minutes.
Okay, let me tell you how to find them. 1, 2, 3, 4, right?
Okay.
How about 5? Well, roughly here. All right, so we'll use I'll use these 5 cards to show the magic trick. So I'll just shuffle them. Don't help me shuffle them. Make everything fully random. So I don't know which card is which, right? I don't know their position. So now we have the 5 cards, and let's just further shuffle them. And let's do, I don't know what they are, right? So there's no way to predict the order. Next, let's just put the cards here. I have a pretty beautiful box here. And inside the box is a piece of paper. There's nothing there. And actually, you'll see there will be something here. So let me just put it here. I actually wrote a prediction, which will appear soon. Let's just put it here. So let's do a top 3 to random shuffle. So with colors. So we take these 3 cards. First, randomize their order, right? You can randomize them. And randomize their colors as well, as we described above. Yeah.
Somebody else. We're doing it again.
Yeah, make sure it's fully random. Just make sure we didn't rehearse. Okay, good. Now, let's put them back as the frozen hail. So these are the 5 cards after shuffling. What is this prediction? I'm a magician, right? So miracles can happen. Okay. Some words appeared. It says, this is an empty box. If you're not convinced, you can check it out. All right, so the words, the piece of paper says ace of hearts is before three of hearts and both are backside up. Do you read it? Let's check that. Ace of hearts is before three of hearts and both are backside up. Ace of hearts. So this is the two, ace of hearts. Wow, ace of hearts is before three of hearts. Both are face up. Oh, face down, I should say. Both are backside up, meaning face down, right? So that's it. Did you catch this? Did you catch it?
That's because they were the frozen tail, right?
Yeah, actually, I created this trick myself. And I made this trick, and let me tell you how I did this actually. So of course, I had written that down before the talk.
Yes.
And in other words, no matter how you shuffle them, it would end up this way. So how I did that? The magic is from what we discussed. The frozen tail remains unchanged. So all I have to do is to make sure the last two cards, meaning the frozen tail, must be ace and three hearts with this order. So how did I control that? You remember I shuffled everything, right? I just put some dots here. Just made some marks. So ace of hearts, I just put one dot. Three of hearts, two dots. So I know which cards they are, right? That's right. So I just put it here. No matter how you randomize the first three cards, the frozen tail remains the same, remains unchanged. Sure. So that's the secret of this trick. Hope you like it.
You're supposed to say it's magic.
Yeah.
It is magic.
Yeah.
Next, Act 3, the magic of the frozen tail. Let's further analyze this frozen tail. So let's define a few. It's pretty funny. We define A0, A1, A2, A3, A4, A5. So these are actually nested sets. Why do we define this? Well, I didn't tell you the general formula, but the general formula is we define A sub n, or A sub u, to be the set of colored permutations for which the largest U labels are still in increasing order and still have color 0. So in this toy case, we have these 6 sets. And as you can easily see, you guys are all mathematicians, I'm sure. You have no problem seeing that. So you're nested, right? A0 is contains A1, contains A5. I'm teaching 108 this semester. If I taught this to my students, I would have to explain everything. For you guys, I'm sure follows naturally. And why do we define that? Well, because we want to define a new statistic called LU. And so before that, let's try to understand the properties of these sets A sub U. So we already defined A sub 2, which is the support of B3, right? This highlighted part. And in general, A sub U is the support of B sub 5 minus U, meaning the frozen tail. When you do top, when you move the top U cards, the remaining cards, the number of the remaining cards should be 5 minus U, right? So that's my definition. And of course, we can compute the order of AU because it is the support of B5 minus U, so they have the same order. And you can easily compute that. We already computed the order of B sub 3, which is 480, right? Just by the same logic, we can compute the general case, A sub U, the order of A sub U, which is this number. And using a calculator, you can easily find the order of all these sets. So let's define this statistic that I mentioned. We set L2 to be the maximum of this set, the largest label such that X is a member of A sub U. So that's actually, it looks hard, but that actually just means the length of the frozen tail. That's all it means. And we have this key identity or key equivalence relation. If X is inside A, X is inside A sub U, I should say here. then this is equivalent to saying L2, the length of the frozen tail, is greater than or equal to U. Let me give an example. For example, let's just take A sub 2. A sub 2, as we defined above, is the support of B3, right? We already explained that. And if X is in A sub 2, that means this property must be satisfied. In other words, 4 and 5 must appear in this order, both have color 0. In other words, the cards must have this arrangement, 4, 5, like this, right? 4, 5. So that is an arrangement in the set A2. You know, if it has this arrangement A2, then the length of the tail, does that have to be 2 by this definition?
No, it could be longer.
Right, yeah, very good. It can be larger, right? It doesn't have to be 2 because the frozen tail, it means by definition, this just means the number of cards that are, that appear in increasing order with color 0. So these are 4 and 5. For example, if 2 is, if 3 is right above that with color 0, then the length by this definition, L2 is 3, right? The length of the frozen tail would be 3. So it's greater than or equal to U, not just equal to U. Actually, this comes algebraically, this comes directly from the definition, the maximum. You can easily prove that through both sides individually. Let's just make use of this identity to get this proposition. Under the uniform measure U, that is the definition of the uniform measure. The uniform measure of the event L2 greater than or equal to U must be equal to that. Let me give you a short proof. The proof is actually very short, and this corresponds to lemma 3.15 in my my write-up, my preprint. This is a special case of this lemma. And because U is uniform, by this identity, we have the uniform measure of that, of course, equals U of AN, right? They're equivalent events. And by definition, this is just the order of AU divided by the entire state space. That's what it means by uniform measure. And we just compute them by substitution, we get what that is, and then subtract successive tail probabilities gives you the point masses, these two. So yeah, I just wanted to introduce that to you. So not that important for this talk. And of course, we can further compute them. So the reason I introduced that is to give you this key result, one of the 2 key results of this talk, because we can show the exact mixture theorem. So this, first of all, we define the k-step law to be M sub k, which is this convolute, this Q superscript M convoluted k times, and so we get this. I didn't prove that. I just directly, I'm directly showing that to you. That's a key theorem. So in general, we have for the top M to random shuffle case, Q superscript M convoluted k times equals this sum. So this is a special case of that. We call that the exact mixture theorem. Later, we'll use that to deduce another key result. And that is this act. Let's move on to the most interesting act, the final one, Act 4, the magic of one statistic LP. So we defined this LP this way as the maximum of the largest label here. And what's special about this LP? Well, let's do some math deduction. Let's by definition, AU is defined as the support, or actually defined this way, as it turns out they're the support, the supports of these sets here. And again, QM, the one-step law, is BM divided by the order of BM, also as we deduced above here. somewhere here. So let's make use of them to see, which where this can lead us. And of course, since this is the support, we can rewrite that as this. Just use A to replace the support and write it as the indicator. This is the definition of the uniform measure. By these two, we can divide this Q by the uniform measure, that is top divided by bottom, gives us this. You can easily tell. I've given you the details. Just this divided by that gives you these two values. And what's special about this likelihood ratio, or these two ratios? Well, by the theorem I just showed you, which I didn't prove, we have this MK. So we just do another substitution. We substitute this MK from this theorem into this quotient. We get this divided by u of x, and I should erase this tape. Divided by u of x, and this then has already been computed right above. So we can do another substitution. In other words, these two together with this theorem give you this result. So what's special about this result? Well, this quotient equals this sum. We can rewrite that as R0, R1, and R2 if we define these sets this way, just by unraveling the definition of the indicator function. So that's what we got. This ratio looks complicated, but it only has three choices, R0, R1, and R2. Let's generalize this result. And of course, we can further compute them by substitution, by substituting the definitions of those P's. And recall that this, for example, this is the probability of the number of empty boxes, or the number of coupon types equal to 0, right? This is K. This is U, as I defined at the beginning. And so we can substitute that. This is not important. And let's give you the general case of this quotient, which is theorem 2, the most important theorem in this talk. It's called one statistic reduction in the toy model. What does that mean? So this likelihood ratio, as we computed above, only has three values. So in general, it is equal to this function, or this value, the value of this function, s sub u. So this s sub u, again, just for the sake of consistency, I use this s to be consistent with my paper. But this s just means r. Like, for example, this just means r0, as we computed above, just the three choices. My point is, the upshot is that this likelihood ratio is a function of the one statistic L2. In other words, this ratio seems complicated, but it depends on x only through L2 of x, meaning the length of the frozen tail. It only depends on the length. It doesn't depend on which x is that. As long as two states have the same length, then this ratio must be the same. Get the idea? So that's the magic of this theorem. And therefore, we can get the last two lines. We can compute this sum and just substitute this value. We get this. And through this identity, we can compute all the distances and divergence, which is what we'll discuss in the last two acts, Act 5 and Act 4 and Act 5. Actually, Act 5 and Act 6. So these distances. And let me directly give you the final conclusion. We have these distances are equal to these values in terms of P and R. It might look complicated, but it takes some time to parse that. We just show you the entire conclusion. This comes from the previous theorem, theorem 2, that I just showed you, by taking the function phi to be these values, together with the definitions of those distances, we get these conclusions. So let me not show you the proof. Let me just directly show you the results. Everything is in my notes. So if you're interested, you can take a look at the notes. Let me just maybe give you one example of the total variation distance. For example, just to remind you of what that is. For example, if we have two probability measures, suppose one is mu, so let's say 0.2, 0.8. The other is u, 1/2. By definition, the total variation distance between the two measures, so they're vectors realized as the output of the probability measures. So the total variation distance between the two measures, mu and u, is just 1/2 times the L1 distance. That's the definition, as you can see on the screen. What is the L1 distance? How do you compute that? Well, it's 1/2 times the absolute value of this minus that, right? The first coordinate minus the second coordinate. Plus the absolute value of 0.8 minus 0.5, right? So let's compute that to get the total variation distance. This is 0.3. This is also 0.3, so it's 0.3. So that's it. And yeah, that's the final act. And yeah, that's basically all I wanted to talk about. For the final act, for the very last one, let me just directly again show you the conclusions, because now that we've computed all the distances, right, as functions, it's very easy to take the limit of each function, right, just by calculus. And those limits are so-called cutoff profiles. And these are as follows in theorem 3. Just by taking the limit of each function, we get those profiles, where those functions are probably something you don't want to look at. Pretty complicated. Yeah, so that's all I wanted to talk about. We have 10 more minutes, so we're in the questions.
How did the magic trick look like that?
That's a question. Which magic trick?
Writing.
The writing. Oh, how did I make it appear? Let me show you the secret. Actually, that's a good question. I have a secret here. If you give me the box, I'll show you how I did this.
I was trying to. I felt it was wiggly on the inside.
It's a magnet. That's cool.
That makes sense. Any other questions?
So earlier you mentioned a function phi that goes from what, r to 0 infinity. What does this function phi represent?
So phi can be any function. And
What does it actually let you do in practice? Like, is this like let you convert this to a statement about any kind of statistics you want, or what?
For example, if you take this phi of t to be t minus 1 plus, this will be reduced to the total variation distance, right? Because by definition, the total variation distance is defined this way. And this is phi.
I see. Okay.
So that's why I thought of using this this general function phi, because this sort of unifies all of the distances.
Yeah.
It's a pretty good trick now.
Yeah. Okay. That makes sense. Yeah.
Any other questions? Actually, I had one last trick that I wanted to show.
Sure.
Last chance. Any questions? This is a pretty interesting topic. So finally, we have one last slide I prepared. Encore.
Yippee!
I promised that I would change the colors back, right? And so let's do that. First of all, let's use this deck of cards. This is a pretty standard deck, bicycle. And there's nothing wrong with this deck. Trust me. And so also I prepared this hat. It doesn't look like a hat, but now it looks like a hat.
Yippee!
I can there's nothing there. Magicians, I'm a magician. Magicians can pull a rabbit out of the hat like this. Is that cool?
Very cute.
And I can pull everything out of the hat. So yeah, not important. Wear it up to make me look more like a magician. So this is a very normal deck of cards. This is I used another deck. This is a red deck, right? every card has the same back, but their faces are all different, right? Every card has a different face. Make sense? And this talk is all about colors. So I'm gonna do one last trick to change colors one last time. I'll need a volunteer to pick a card from this deck. Who would like to do that? Yeah, very good. You can use your finger to touch any card. Just touch it. This one? Okay. Remember this card, okay? Called the Jack of Hearts. And next, I'm a magician, so let's change the colors of the deck. This is a red deck, remember that, right? Let me change the color to blue. 1, 2, 3, ta-da, everything. Except for one card. Do you believe that? Except for one card, which is your card. So let's try to find out. Wow, there's a red card. Right, everything else is blue, except for one card. Do you remember which your card is?
All right, the Jack of Hearts. Wow.
Wow, okay. You did that.
Okay, that one's I haven't finished yet. I promised that I would change everything from red to blue, right? But this card is still red. Everything else is blue.
Yeah.
Look, 1, 2, 3. Everything is blue. So everything is blue.
Whoa.
Okay.
That's it. Thank you for coming. A wonderful evening. Take care. Stay wondrous.